Welcome back. In this class, I will continue with the introduction of polymers. I will begin with classification of polymers. Now, at the very beginning, you should remember that there has not been, or still there is no single method for polymer classifications which is generally accepted. What I will do, I will list all the various ways of classifying polymers. Now, I do not expect student to remember a question how many ways a polymer can be classified, but students should be aware of the terminology which are used in these various classifications, so that when they come across these terms, they should be able to relate the meaning of this term. Let us start with the classifications. Classification can be done how, where from a polymer is originated. In the last class, I have said that polymers can be originated from natural sources, and I also said that those are minor class of polymers. Majority of polymers are synthesized in the lab or in a plant from most cases petroleum resources, and some cases from natural resources, natural resource derived monomers. So, we can classify as a synthetic polymers, the polymers we synthesize in the lab, or we can classify as the natural polymers, in which case polymers come from nature. For example, polysaccharides, which represent cellulose, starch, cotton, biopolymers, proteins, nucleic acids, wool, silk, and so on, and say natural rubber, cis-1,4 polyisoprene. Some cases we take these natural polymers and we modify these polymers synthetically for a particular reasons, for a specific applications. In those cases, we can term those polymers as semi-synthetic or semi-natural in any of the ways. So, third category could be semi-synthetic polymers, which are chemically modified natural polymers. Synthetic polymers can be classified as organic polymers, the polymers which are made from carbon, nitrogen, oxygen, and hydrogen, and as inorganic polymers, where beside these elements carbon, hydrogen, nitrogen, oxygen, you have silicon, phosphorus, boron, sulfur, such elements in the polymer molecules. For example, siloxanes, silanes, silicones, phosphogenes, these are the examples of inorganic polymers. Synthetic polymers can be classified as homochain and heterochain polymers as well. Homochain polymers means a polymers which has a backbone of only carbon, C. For example, polyethylene, polypropylenes, these are made of polymer. The polymer chain is consists of only C backbone, whereas in case of heterochain, besides carbon you might have nitrogen, oxygen, and other heteroatoms. For example, nylon have nitrogen, oxygen along with carbon. Polycarbonate has a carbon plus oxygen in the backbone. Polymers can be classified as according to the chain structure. It can have linear chains like this. It can have branch chains, like you have this linear polymer plus you have these bunches you can have branches like this, or you can have branches like these are available. Now, the main difference between these three branch chain, all of these three are called branch chain polymers. In this case, the length of the branches is much smaller compared to the length between two branching points, whereas in this case the length of the individual branches is comparable to the length between two branching points, and in this case branches also have sub branches. So, in this case we call this as short branched chain, short branch, and this is long branched, and this is hyper branched. Now, a special type of branching, if you have polymer like this where branches is coming from a single point, you get a star polymer. Now, you can also have network polymers. For example, if I have different chains in a polymers which are connected, covalently connected, like this, and so on, then this entire polymer is cross linked, so that the individual chains does not exist. If you move one chain, the entire network will come along with it, and this is called polymer network or network polymer. Now, you can have mixture of such networks in a same sample. You have mixture of, if you have mixture of two network, then this network will penetrate with each other, then we call this as interpenetrating network. If I just show in some colors, different colors, you can have two networks intertwined with each other. So, you have interpenetrating network, and in another case you can have one of this network as one of network along with long chain linear polymers. In that case, we call that system as a semi interpenetrating network, where one of the constituents is linear chain polymer, another one is network polymers. So, in that case we call it a semi interpenetrating network, and when both the or more than one networks are intertwined with each other, then we call it a interpenetrating network. Polymers can be classified according to the monomer compositions. Homopolymers, if you have a monomer represented by A and linked with each other, then we and so on, we call as a homopolymer. You can have polymers made from two different monomers, say A and B. As I said in earlier class, example given polystyrene and polymer made up of styrene and MMA. Then you can have copolymers. Now, copolymers can be different molecular structures. They can be present in the polymer chain randomly with no order, something like that, where you do not have any order of placement between any order of placement of the monomers, they are present randomly, then we call random copolymers. If they are present alternatively, then we call alternating copolymer. Now, if these two monomers are present like this, where it is sort of combination of two small blocks of A and B. So, it is like oligomer of A or polymer of A, which is linked with oligomer or polymer of B. Then this is example of block copolymer, and there is another version of the block copolymers where you might have a backbone of homopolymer, so on, and from which you have maybe hanging chains of another block. Then we call this as a graft copolymers. You can extend this in the 3D and have this as a brass polymer, where you have a backbone, a two dimensional A, and these brasses are hanging from the base. So, you can have brass polymers and so on. We can classify polymers as a chain configuration. For example, if I take a monomer like this, it can make polymers in two ways. And so on, where if this is a head and this is a tail, this is head and this is tail, then polymer is formed by linking between head and tail and so on. So, it is a head and tail polymer. Now, these polymers can be also imagined like this, where head and head is linked, and then or the tail and tail will be linked next monomer. So, that is a head and head to head polymers. Now, in practical sense, in most of the cases, exclusively almost every cases, when you synthesize a polymer, you get head to tail polymers, and you rarely get, unless you make a specific arrangement to make such a polymer, you do not get head to head polymers. You can have polymers as a geometric isomers, like in this case cis polyisoprene, all the monomers are arranged in a polymer in a cis arrangement. Now, you can have them in trans arrangement or a cis trans arrangement as well. So, that gives you geometric or cis trans isomers. You can have stereoisomers, or which we call in polymer term different tacticity. If in this case the chiral centers or these have similar geometries, all these monomers are linked with same geometries or stereochemistry, then we call this as isotactic. If they have alternate stereochemistry next to monomers or next to the repeating units, then we call syndiotactic, and if the stereochemistry of the repeating units are randomly placed, there is no order, they are named as atactic. So, if the repeating units have same stereochemistry, all the monomers, all the repeating units have same stereochemistry, called isotactic. If they are alternate one after one, then we call syndiotactic, and if there is no order or it is placed random, then we call it as atactic. Polymers can be classified as thermal behavior as well. Now, you commonly think polymer, where you can take polymer, a polymeric material, and then heat it. On heating, it will become a fluid, a melt, and you give them a proper shape and cool them. It will harden and occupy or get that the shape you are looking for. Similar like a wax, where you melt it and it, when it cools, it takes up the shape of the container you place the wax. These are called thermoplastics. Plastics is meaning formable. So, it is a polymeric materials which can be formed or can be transferred into different shapes by heating and subsequent cooling, and this cycle can be done several times. So, you can make a polymer of definite shape, and later on if you melt it again by heating, and again you can reshape it, give it reshape. Okay, so that is these polymers are recyclable. Another class is thermosets, where a polymers is made in situ. You start with small molecules, monomers, as a low viscosity liquid, and then put it in a container and then cure it by heating or doing some chemical reaction. By that, doing this reaction or by heating, it forms a cross-link network. The terminology I mentioned in last slide, last page, where these polymer chains are networked, they are cross-linked and frozen. So, once the polymer material has taken the shape of the container where you are doing the curing process, what happened, you cannot remelt it, because they are cross-linked. The polymers cannot be moved around with each other, so they cannot be melted by heating. So, they are frozen. They are like having infinite molecular weight cross-linked polymer network. Thermoplastics can be amorphous or semi-crystalline. In case of amorphous polymers, where polymer chains, long polymer chains are placed randomly with no order, and in case of crystalline polymers, you have the chains placed in like a crystal, they are having a definite order. We know the crystal, the molecules are arranged in a definite order. So, in a crystalline polymer, you have the polymer chains placed in definite order, but it is impossible, or it is highly unlikely that you can make a perfectly crystalline 100% crystalline polymers, because polymer chains are very large, they are flexible. It is almost impossible to align all the chains one after to make a 100% or perfect crystalline polymers. So, when we talk about crystalline polymers, there is a mixture of crystalline regions and amorphous regions which do not have any order. So, in more technical sense, it is called as semi-crystalline polymers. Semi-crystalline polymers means a polymers having both crystalline regions and amorphous regions. Amorphous polymers are mostly clear and crystalline, because these domains, crystalline domains, will scatter light. They are, depending upon the extent of crystalline, they can become translucent or opaque as well. We will talk about this in a little detail in later. We talk about the polymer properties. Thermosets, which talked about in the last page, they can be glassy or elastomer. As I said, they are cross-linked network, and if these chains between network, they have flexibility, which happens if the temperature at which they are, it is above their glass transition temperature. I will talk about glass transition later, more detail, but at present just glass transition means the temperature at which they becomes flexible. Okay. Now, if these chains are flexible in the temperature you are working, then they can be stretched. They can be stretched, and as soon as you remove the stress, they will come back to the original form. So, it is like rubber. So, you have a elastomer. Now, if these chains are below their gas transition temperature, that means they do not have any flexibility in the temperature of operation, then you cannot stretch the polymers, because they do not have any flexibility in the thermal motion you are talking about. So, you cannot stretch. So, they are like glassy thermostats. Polymer can be classified according to the applications. They can be plastics, fiber, or elastomer. If they are defined more from a stress strain curve, from their mechanical properties. If I plot strain versus stress of a polymer sample, then elastomers are like, with small strain you can, with a small stress you can strain the polymer samples much more. You know how the rubbers work, with small pull they stretches out longer time. So, this is like elastomer. With a small stress you can strain the sample much more. Fibers is the extreme case, other side. You take these fibers and to strain it, that means to stretch it little bit, you have to apply very high stress. So, you have situation something like this. So, to strain a fiber you have to apply a very high stress. Plastics are somewhere in between. This is fiber, elastomers, and this is plastics. Now, after some time plastics yields, I will talk about more about these terms, and it becomes easy to strain. If you have this packaging films, you have seen probably that when you stretch at the beginning it takes a little difficult, you have to give a lot of force, but once it starts stretching, that means the samples yielded, then it becomes quite easy. So, that is the example of plastics which gives away this type of stress strain curve. We will talk about this in more when we come back to the mechanical properties of the polymers. Polymers, according to applications, they can be named or classified as coating, gels, and additives, and so on. These are basically depending upon the applications where you are the polymers is find application. Based on the volume, performance, and price, polymers can be also categorized into three classes. Commodity polymers, the polymers which you see in everyday life, all the times, the bottles, buckets, and shoes, clothes, and all these things, they are having much volume, used heavily, and so the prices is low, and performance is also not so good compared to the other classes of polymers. And the other two is engineering polymers and high performance polymers, and the price in these three, the volume goes up like this. You have more volumes for commodity polymers, performance goes up in this direction. The high performance polymers are having the highest performance, and so does the price. Nothing comes cheap. So, as you get more performance from the polymers, you get you have to pay for more. So, prices also go up. Now, I will come to the most important classification of polymers. This is last and most important. It is based on the polymerization mechanism and the reaction product. Depending on the reaction product, you can classify polymers as addition polymers or condensation polymers, and depending upon the mechanism of the polymerization, the process which polymers are synthesized. It can be classified as chain and step polymers or chain growth and step growth polymers. This term addition and condensation, this classification was originally proposed by Carothers in 1929, and as the name suggests, the condensation polymers are synthesized by condensation reactions of the monomers. You know condensation in organic chemistry. Condensation reaction means a reaction between two molecules and subsequent elimination of small molecules. If we are talking about making ester between acid and alcohol, you make ester, removal of a water molecule. So, the condensation polymers are the polymers where you make the polymers are synthesized by condensation reaction between the monomers. I will give you a specific example. For example, if I take, I will just give you write a general way now. So, if I have plus these two reacts, n molecules of this and n molecules of this, it will give you polyesters. To give you more example, I want to make polyamides. So, I take this molecule and n molecules of this, which gives So, in both the examples, in the last case when we made polyester, or in this case we are making polyamides, we have is elimination of these small molecules, in this case water. Now, we can extend these examples. Remember, in the last class we talked about synthesis of polycarbonate from phosgene and bisphenol A, where the compound or the small molecules which eliminated what HCl. So, in all these are all examples of condensation polymers, where the polymers is made from condensation reaction of the monomers. Now, in this particular case, for forming polyamides, you can make this from diamine and diacids. This can also be made from other variation of these monomers like diamines and diacyl chloride. You can land up in same polymer along with different small molecules, or it can be this polyamides can be synthesized by self condensation of amino acids, which will make polypeptides. So, same type of polymers, in this case polyamides, can be synthesized by different set of monomers or self condensation of these amino acids. Now, what in addition polymers, they are defined as the polymers which are synthesized by addition reaction. Into addition reaction means where monomers are just adding with each other and making polymers without elimination of a small molecules. Now, these natural polymers, say like cellulose, how do you define, which class they belong, whether it is addition polymers or a condensation polymers, because they are not synthesized in the lab. So, we do not know the constituent from or the monomers from which, or the type of reaction, there is a condensation reaction or an addition reaction by which they are synthesized. But looking at the structure, what we can anticipate or we can imagine or we can hypothesize are monomers from which they have been synthesized. They can be synthesized in the lab, or in other words, the polymers can be degraded to some other small monomers, monomeric molecules, hypothetical monomeric molecules from which these can be synthesized. We will give a proper structure and so that get now this is cellulose. Now, it can be degraded easily to this following molecule. Which is nothing but glucose. So, this is, though this is a natural polymers, but you can imagine a monomers like this from which they are formed, and in this case, because you imagine or you hypothesized that these are formed through a condensation reaction, most of these natural polymers are classified as a condensation polymer. Now, these two polymers, condensation and addition polymers, they are often used synonymously with chain growth and step growth polymers, because most of the condensation polymers are synthesized by chain growth polymer mechanism, and addition polymers are made through a chain polymerization mechanism. But this is not always the case. The students should not confuse, should not equate the terms with addition polymers with chain polymers or condensation polymers with step polymers. Now, let us example of polyurethane. Polyurethane can be synthesized from thiol and diisocyanate. continue this here. So, this is a polyurethane which is synthesized from a diol and diisocyanate. Now, what do you call this as addition polymer or a condensation polymer? According to the organic chemistry definition, this is an addition reaction, this is not a condensation reaction, but if you compare this polymer along with the other condensation polymers, they have similar backbone structure. Like if you compare with polycarbonate, this has this structure. If you talk about polyester, you have this. You talk about amide, you have this. So, this structure, the functionality in the backbone, they are much more similar with your condensation polymers rather than the addition polymers. Most addition polymers have a backbone of carbon. So, though according to the definition of addition polymers, it should be addition polymers, not the original definition of addition polymers. It should be addition polymers, not a condensation polymers, but you can yourself justify it being a condensation polymers rather than a addition polymers. So, the original definition of addition and condensation polymers are modified, and now the condensation polymers are polymers where you have a functional group like this Z, where Z could be any of these. It could be oxygen, ether, it could be ester, it could be amide, it could be any of these things. Okay. So, the original definition of addition and condensation polymers, where addition was the polymers which are made from addition reaction, and condensation polymers were the polymers which were synthesized from the monomers by condensation reaction, got modified, and now condensation reaction is where the polymer contains or a functional group at the backbone. You can have a general representation of the backbone structure like this, where Z represent any of the functional groups we talked about, and any polymers which do not have these structures, we call them as a addition reaction. Now, that did not solve the entire problem. If we give the next example, that will be clear. We talk about very old phenol plus formaldehyde reaction. This gives a polymer like this. Okay. Now, with the original definition of addition and condensation polymers, you will definitely classify as a condensation reaction, because in this reaction small molecules are coming out. So, this polymer is formed by condensation reaction, but the definition we came up in the last a few minutes back, where condensation polymers are this represented by this, and anything else are called addition polymers. If you talk about the backbone of these polymers, this is the backbone. Okay. So, this is the backbone in this case. What do you see here? There is no functional group in the backbone, it is all carbon. So, according to the definition just now, it should be a addition polymers, not a condensation polymers, but you can clearly see that, given a choice, you will probably classify this as a more of a condensation polymers rather than a addition polymers. So, now the definition is or the classification is done by summation of conditions, with the conditions. For example, condensation polymers are polymers which fulfill any of these criteria. One is made for condensation reaction, or it has functional group in the backbone, or it can be degraded to hypothetical monomers from which they can be synthesized, at least imagined that they are formed by condensation reaction or by elimination of some small molecules. And if any of the polymers does not fulfill any of these criteria, then we call them as a addition polymers. So, once again, at present you should classify condensation polymers if it fulfills any of the conditions. It is synthesized by condensation reaction, or it has a functional group in the backbone, or you can imagine that it has been synthesized from a monomers by elimination of small molecules. And if any polymers which does not fulfill any of these criteria, we classify that as a addition polymers. Now, we will come to the mechanism of polymerization. These two type of polymer, this classification, chain growth and step growth polymers. You take example like I took in the class, styrene. You get polystyrene. I can write a general structure like this: CHY, CH2, gives a polymers. Now, how do you think that these polymers are formed? In this case, these polymers cannot react with each other just by itself. So, you need a initiator, whether the initiator is a radical or a cation or anion, it has to initiate a chain. So, if you react with, say, this is initiator, you get an active center here, and on which the second monomer gets added, and you have this. Don't consider this dot. So, how this polymers is getting formed? You have active center on which a next monomer is getting added, and third monomer will be added in there. So, you have this type of the polymers are getting formed in a chain reaction. Now, in a normal case, in general case, the formation of these active species, they are much slower compared to this step, which basically the propagation step of the polymers by which the chain is formed, which means as soon as this active species initiates the is formed, it initiates and the chain formation is completed. I will come to the more detail how this gets terminated and all these things, but for time being you should understand that as soon as this, more often as soon as this active center is generated, it reacts, initiate the chain and the chain is formed. So, the more and more active centers, more and more initiator gets generated in a system, more and more chain formed. So, if I plot conversion, say percentage, conversion means the fraction of monomers is reacted or disappeared from the reaction medium with the molecular weight or the size of the chain or the size. What do we expect with time? And conversion is also, you can also write time, with more time you will. Let us talk about conversion now. So, at the beginning, when this initiator is formed, as soon as the initiator is formed, in most cases as I said that it immediately start the activation and initiation and then complete the chain. So, you have large molecular, at the beginning itself you have large molecular weight. The more and more this initiator generates in the system active species, more and more chain gets. So, at the very beginning itself you get a high polymer, very high molecular weight polymer in the system, and the more and more active species get generated, more and more monomers reacts. So, more and more polymer chains are formed. So, what is happening here at the very beginning itself, the polymers, large polymer chains are forming, and as time goes, the conversion happens, more and more reactor, you get such, the number of such polymer chains increases with conversion. The more conversion means more number of chains are, polymer chains are getting formed. It is not the molecular weight is increases. So, with conversion, more and more polymer chains are getting formed. So, if I stop say the reaction somewhere here after say 10% conversion or 5% conversion, what do you see in the, what do you expect in the system mixture? 5% conversion, that means 90% monomers are left in the system. So, you get plenty of monomers, 95% monomers. What about the fate of that 5% monomers which got converted, which got reacted? This is almost all of them has formed long chain polymers. So, along with that 95% of monomer present in the system, we will get the other part as a long chain polymer molecules. So, you get, even if you stopped at the very beginning with a very low conversion at say 5%, you see high molecular weight polymers, monomers and the initiator in the medium. If you stop here at a 95% level, then you see lot of polymers, large chain polymers and a small amount of monomers and the leftover initiators. Okay. Now, I will go to the step growth polymers. And then come back later to compare between these two. Now, say I take a monomer ANH2, okay, say RNH2 and R dash COOH forming polyamides. I write this as AA and this as BB. This is diamine and this is diacid. These two monomers can react by itself. You do not need any external initiator like chain polymerase. It is a matter of fact that you need catalyst to accelerate the reaction, but you do not in true sense you do not need a external initiator like in the case of chain polymers. Now, how this will react? How will form polymer? First, this will react, two monomers will react and form like this, species like this. So, this is dimer. Now, this dimer has a choice of reacting with itself or has a choice of reacting with any of the two monomers. If it is reacted with this, so you get A, B, B, again AA. If it reacts with this, if it reacts with this, then you get BB, AA and BB. Okay. Now, if it reacts with itself, then you get A, BB, A, BB. So, you form these trimers. This is a trimer, consists of 3 monomer molecules, and this is tetramer, consists of 4 monomer units or structural units. Now, once you form the trimer, the options increases. It can react with the monomer, it can react with any of the dimers, or it can react with the trimer itself, making the possibilities more and more. If it reacts with monomer, it will form tetramer. If it form with dimer, it will form pentamer. If it reacts with itself, it will form hexamer. And imagine once you form the tetramer, what will happen? It can react with monomer, dimer, trimer and itself, forming dimer, forming pentamer, hexamer, heptamer and so on. So, in the chain reaction, you have the long polymer chain at the beginning itself. But in this case, you are not getting the long polymer chain at the beginning. What you are getting, the polymer chains are forming in steps, dimer, trimer, tetramer. And because this monomers can react, this functional group react, they are reactive functional group. So, they will react immediately. So, the conversion of polymer, conversion of monomers will be very high even at the beginning, forming dimer, tetramer or these small oligomers. So what happened? Only at the end of the polymerization, you will see a long polymer chains are forming. Unlike the chain polymers, where you have even a small conversion, you get the large polymers. So, if you stop the reaction in the beginning, you will see lot of this high conversion, but lot of these small oligomers. So, what in the next class, I will continue with this condensation polymers and talk about the compare between the difference between chain polymers and chain growth polymers and step growth polymers. Then it will become more clear the difference in the mechanism of these polymers to polymerization medium. And in the next class also I will talk about, I continue with the introduction, more talk about we will talk about the nomenclature, how polymers are named, and also I will talk about give you a perspective of the molecular weight of polymers. You have learned that the polymers have large molecular weight, and invariably either of this synthetic process you land up in a distribution of molecular weight. Not all the polymer chains are of same size or same molecular weight, they will be of different molecular size, and I will talk about what the molecular weight and why you need more definition of molecular weight and so on. So, we will come back to the next class with this.